Here's a non-mathematical problem about what happens to a charge that you put on a conductor, like this conducting block here. So it says, you got a charge on a conducting block. Of course, you know what's going to happen is it's going to move to the surface. And if the charge is free to move around in a conductor, then what it gets to get as far from itself as it can, so it's going to run to the surface like this. However much you add, it'll all go to the surface. And we know that for conductors, it does that to keep the E field inside equal to 0. Let's see what other things we have to remember. So one statement is E outside the surface is perpendicular. And that's actually true. Remember, the charge inside the metal moves to make E equal 0, but it's also true it moves on the surface to keep the E field perpendicular to the surface. So if we drew our field lines like that, they might bend around like something like this, but they will always be perpendicular right at the surface. And the reason is, if you built up a field with a horizontal component to the surface, right at the surface, that would cause free charges to move. They'd move in a way to cancel that horizontal field. So in the end, you could only have a vertical field, or a perpendicular field right at the surface. So we're trying to figure out which of these is true. This is definitely true. This is always true in electrostatic equilibrium. This says the E field is uniform on the surface. So parallel is fine, but does it always have the same magnitude on the surface? And that's actually not true. That's true for a sphere, because everything is nice and symmetric. So everywhere you go, the field line would have normal density. But we thought about and we read about in the book that the charge tends to collect at corners. So you actually get denser field lines at corners than you do on flat surfaces, on an irregular object that's not spherical. So it's actually not true. The E field is not uniform on the surface. It gets sharper at corners. It's kind of hard to show it mathematically, but that's why it's always stated clearly in the book. And finally, the E field is a constant inside the block. Well, you got to read carefully. It actually says it's a non-zero constant. It is true that it is a constant. That constant must be 0. E is constant, but E does not equal 0 inside the block. And that is not true. The E field is actually numerically, quantitatively 0 inside the block. The one thing this might be kind of making you think of or tricking you, if you thought this was true, the potential is constant inside the block. So the potential is just or the E field is the rate of change of the potential. So if the potential is constant, the rate of change is 0. So you can have a potential here, you just can't have a field. So the answer is that only this is true.